In this video, we're going to talk about integrals that lead to inverse trig functions. So this is going to get pretty involved. First, let's just remember the derivatives of the inverse trig functions. And so they're listed here in the white. The derivative of arc secant of u is du over the square root of 1 minus u squared. And going across, the derivative of arc cosine of u is just the negative du over square root of 1 minus u squared. The derivative of an arc tangent of u is du over 1 plus u squared, and the derivative of an arc cotangent is the negative of that. The derivative of an arc secant of u is du over the absolute value of u times the square root of u squared minus 1, and the derivative of arc cosecant of u is the negative of that. So let's slide down and look at the yellow a minute, and we'll talk about our integrals. So we see that if we know the derivative of these, since the derivative of arc sine and the derivative of arc cosine are only a sign different, rather than integrating something like this and saying it's going to be an arc cosine, we're going to move the negative outside and just say that it's going to be a negative arc sine of u. So we are only going to get, because these three derivatives on the right are only different by a negative sign than the three derivatives on the left, we are going to only get three antiderivatives or integrals of these expressions. So we're only going to get an arc sine, an arc tangent, or an arc secant. Now, the thing that I want to point out is, two of these have radicals. And you may think that there's that the most important distinguishing characteristic is this u, but we are going to see some examples of where it might be kind of surprising, and that's going to be disguised. A more reliable determinant of whether it's going to be an arc sine or an arc secant is going to be the order of this subtraction. So when you see a constant minus some function of x, that's going to lead to an arc sine. When you see a function of x and then a minus some kind of constant, that's going to be a more reliable signal that we're going to get an arc secant. We're going to talk about this in much more detail. And of course, the arc tangent is the easiest to identify because it has no radical at all. Now notice that the first one is not going to be a good candidate for a straightforward u substitution. That is, we can't let u be the inside of the radical because there is no, if we said that was like an x squared, if u was x and you had an x squared, there is no power of x in the numerator. So that's how you're going to distinguish between whether it's going to be a u substitution that leads to a power function or an inverse trig function. We'll talk more and do some examples. But I want to talk a little bit, it's a little confusing about why, if we look at the arc secant and its integral and derivative for a moment, it can be a little confusing. And that's why I have it starred in red up here. So the derivative of an arc secant doesn't have an absolute value in the original, but it does have an absolute value in its derivative. The integral coming down here does not have an absolute value in the integrand, but it has to have an absolute value in its integral, in its antiderivative. So I'm not going to get real deep in the weeds here, but we can at least see this and kind of hopefully understand, or at least appreciate that those absolute values make a difference. Now, just to graph an arc secant is not an easy thing, even when we are going to use our calculator. So I'm going to just call this arc secant of x. So not going to make it a chain rule here. Now, to graph this on our calculator, we have to do a little bit of work here. So here's what we're going to have to do. Let's take the secant of both sides, So that's going to get us secant of y on the left, and the secant of the arc secant of x is like f of f inverse. That's going to get us just x. We'll recognize that secant of y is 1 over cosine of y. Then we'll take the reciprocal of both sides and get cosine of y is equal to 1 over x. And then we'll take the inverse cosine of both sides and see that the arc secant of x is the same as the inverse cosine or arc cosine of 1 over x, the inverse cosine of the reciprocal. So the way we're going to graph y equals arc sine, or arc secant of x is to go to our calculator and graph y equals the inverse cosine of 1 over x. When you do that, you're going to see, it's not real easy to decipher, but you're going to have a point that when x is negative 1, the arc secant of negative 1 is pi, and then it's going to approach y equals pi over 2 as a horizontal asymptote. At x equals 1, the arc secant of 1 is going to be 0, and it's going to approach that horizontal asymptote of y equals pi over 2 going to the right. Now, while you have that on your calculator, you can go back and graph y equals the arc secant of the absolute value of x by putting on your calculator the inverse cosine of 1 over the absolute value of x. When you do that, you're going to see that the positive stuff remains the same, but that negative stuff is going to get reflected in that line y equals pi over 2 and look like that. I'm going to redraw the right side a little bit better so it looks a little bendier. So it's going to look more like that. Okay, now we'll come back and talk about this, but let's now graph on our calculators. We can here, let's graph y equals 1 over the absolute value of x times the square root of x squared minus 1. So if you put that on your calculator, you're going to get a vertical asymptote at negative 1, and your curve is going to approach that vertical and horizontal asymptote to the left of negative 1, and it will also approach x equals positive 1 and y equals 0 as vertical and horizontal asymptotes on that right side. Now you can see, hopefully here, that the connection between these two curves are that when you take the derivative of arc secant of x, that at least here on the left, that this is always increasing, which means its derivative should be positive all the time, that is above the x-axis. Well, at least it does that. Meanwhile, over here, you can see it's also increasing, so also this graph of the derivative should be always positive and above the x-axis. So you can see that this is going to be the derivative of our arc secant of x, and it does need that absolute value. Now, let's graph over here y equals, we're going to say 1 over the x not in absolute values of x squared minus 1. And when we do, we'll see that we get this part on the left now is going to be negative, whereas this part on the right remains above the x-axis. I bumped it. So it's above the x-axis, that is positive. So now if you look at the derivative of, I lost my pen, let me get it back. If we look at the derivative of this, it's going to match that because these derivatives, tangent lines, are all going to be negative, which are going to match this always being negative. and these are still positive, which matches that. So if the derivative of this green function is that, then that means the integral of this is that. And that's why when we integrate this, we get the absolute value there. So I hope that makes sense. That's about all I really want to talk about there, is to kind of give some, at least a visual explanation for why we have that. In the most generic case, we don't need absolute values in the arc secant, but when we take its derivative, it does have to have an absolute value. When we integrate, we're not going to restrict what we have there, but that means you do have to have an absolute value in the integral. These you are going to have to know from memory. So added to our growing list of things we have to know from memory. All right, let's see how this works. Now, when we do this, we're going to have to first look at this integral in green, the dx over square root of 9 minus x squared. And we look at that and see that, kind of our checklist is, if we try to make a u substitution of 9 minus x squared, that means that du is going to be a negative 2x. But you can see there is no power of x in the numerator to match that du. So that is not going to work. So once we have ruled that out, the next thing we think is, I bet this is going to be an inverse trig function. Now, we see it's got a radical, so that means it's not going to be an arctangent. So now we're debating, is it going to be an arcsine, or is it going to be an arc secant? We see the order of the subtraction is a constant on the left minus the x, minus the function. So that tells us we think it's going to be an arcsine, and it will be. So now to get our arcsine, I'm going to scroll up for a moment. We want to match this 1. That's what's going to drive this train. So we are going to, inside this radical, we're going to factor a 9 out. So this, I'm just going to look at the radical for a minute here. So we're going to factor a 9 out, and that's going to leave a 1 where the 9 was. When we factor a 9 out of the x squared, that's going to make it be x squared over 9. Right? Can you see that if you were to distribute that 9 back to there, it would cancel and get us back the x squared we started with. Okay. Now, when we have the square root of a product, that's the product of the square roots. So that means our 9 can come outside of that radical as a 3. So that's going to be a dx over 3 times the square root of 1 plus x squared over 9. Now, that 3 in the denominator can come outside our integral, so it's going to be 1/3 integral dx over square root of 1, and I said a plus there, but that's really a minus x squared over 9. Okay, now we're making progress. It has the form now of 1 minus u squared inside that radical. That means our u squared is the x squared over 9. That means our u substitution is going to be x over 3. See how that works? Because then u squared is x squared over 9. Now we are thinking of that as a 1/3 times x, which it is. So that means du will be 1/3 dx, and that means that dx will be 3 du. So our integral now is going to look like the 1/3 we pulled out. The dx we're going to replace by 3 du. We now have the square root of 1 minus u squared. We're almost there. The 3 is going to come outside and cancel with that 1/3, and we have finally gotten the integral that we want, du over the square root of 1 minus u squared. So that is going to be an arc sine of u, and you could also call it an inverse sine of u. That notation is interchangeable. Those are equivalent. And so then we're going to go back to our x's, and so our answer to this integral is going to be the arc sine of x over 3 plus c. Interesting stuff. Okay, going to scroll up. Here's another one. Now, again, the kind of checklist we're building in our head is we say, well, I wonder if we could call u that entire denominator. If we did, the du would be 8x, which means with the constant we can fix, but we have to have a power of x, but there is no power of x there in the numerator. That we can't create, so that means that's not going to work. So we don't really have any other good options, so we're thinking it must be some kind of inverse trig function. So since it does not have a radical, our really only option is we hope this will be some kind of an arctangent. So to make it be an arctangent, we need to make that be a 1. So we are going to, in that denominator, factor that 3 out. That's going to turn that 3 plus into a 1 plus. That's what we wanted. And that's going to make that be now a 4/3 x squared. Not pretty, I agree. The 3 in the denominator we can pull out and make 1/3. We now have the integral of dx over 1 plus 4/3 x squared. This is progress. We're trying to envision this as a 1 plus u squared. So our u is going to be the square root of 4/3 x squared. That's going to be 2 over the square root of 3x. No need to rationalize here. It's messy enough as it is. That then means that du will be 2 over the square root of 3 dx, and that leads to dx being the square root of 3 over 2 du. So our integral is now going to have that 1/3 we pulled out. The dx is going to get replaced by the square root of 3 over 2 du all over that 1 plus u squared. The square root of 3 over 2 will pull outside, and so now that's going to look like, I guess, the square root of 3 over 6, and the integral is what we wanted to get. That is going to give us our arctangent. So that's going to become the square root of 3 over 2, over 6 rather, the square root of 3 over 6, arctangent of u, and then we'll go back to our x's. So I keep wanting to make that a 2, but that's really a 6. So that's going to be an arctangent of, and that's going to be our 2 over square root of 3x plus c. Okay, kind of getting a little feel for it. Let's scroll up now. Again, if we think, at least in our head, can we make u equal to the inside of that radical? Then the du would be an 18x dx. Now we do have an x, but it's not in the numerator where we would need that du to appear. So that's definitely not going to work. Now, we're hoping this is going to be some kind of inverse trig function. Now, it does have an x, which is what we want for an arc secant, but more conclusively is that in the radical we have the stuff with x in it minus the constant. So that is a more reliable look for, a more reliable clue. So we're going to try to make this be an arc secant of u. So we have to first make this be a 1. So as we have seen before, we're going to, inside the radical, factor out a 1/4. Now to factor out a 1/4 to factor out a 4, not a 1/4, sorry. To factor out a 4 is to divide by a 4, so that's going to make that be a 9/4 x squared minus 1. Then we can pull that 4 outside the radical as a 2, pull it all the way outside the integral as a 1/2. And so now we have dx over x square root of, and we've got 9/4 x squared minus 1. We are seeing the inside of that radical as a u squared minus 1. So that means u will be the square root of 9/4 x squared, which is going to be 3/2 x. That means the du will be 3/2 dx, and the dx is going to be 2/3 du. Okay, so we have this 1/2 integral. The dx will replace by a 2/3 du. We still have that x. We're going to have to deal with that in a moment. And our radical has now become u squared minus 1. We're making progress. We got the 2/3 we're not worried about. We can pull that out. We've got the square root of u squared minus 1. We have the du. This x is a problem. We can't have x's mixed in with u's, so we come back to our u substitution and solve for x and say that x is equal to 2/3 u. So we are going to replace that x by a 2/3 u. So that's 1/2 integral. We have our 2/3 du. The x we had in the denominator we're going to call 2/3 u, and we have our u squared minus 1. Well, things worked out very nice because those 2/3 will cancel each other. So the good news is we have 1/2 integral, and we have now created the integral that we were hoping to. That is our arc secant, so it's going to be 1/2 arc secant of the absolute value of u plus c, which when we go back to our x's is going to be the arc secant of the absolute value of 3/2 x plus c. A lot to these problems. Okay, now this one is a new kind of challenge here. We can't, if we tried to make a u substitution where we had the whole e to the 4x minus 1, the du, we would get the same exponential times, with a chain rule, the derivative of the exponent, and we don't have any exponential there to account for that. So that's not going to work. So, I don't know, I guess our only really option here we have is to hope for some kind of an inverse trig function. Now it may look like that's going to be an arc sine because we don't have anything outside there, but our more reliable indicator is the order of the subtraction. And since we have the function, something that we're going to make into a u squared minus a constant, this is in fact going to lead to an arc secant. Crazy. We already have the one that we would like, so we're ready now to see this as u squared minus 1. That means now, think about our property of exponents. When you square a power, so we're going to actually call u e to the 2x, because when you square that, you multiply exponents, and that's how we're going to get that e to the 4x. So u is the e to the 2x. du, its derivative, will be the same exponential e to the u times the derivative of the exponent. So the dx is going to be du over 2e to the 2x. Okay, this gets kind of interesting. So our integral, we're going to replace that dx by du over 2e to the, I'm going to write it maybe this way. Let's say we're going to think of that dx as being du over 2e to the 2x. We've got a square root of u squared minus 1. Now, when you look at that, you can see that our u is right there. So we can actually pull that 2 in the denominator all the way outside the integral as a 1/2. Now we've got a du in the numerator, and this e to the 2x we're going to call u, and there's our square root of u squared minus 1. Isn't that crazy? That is our arc secant. So we're going to get 1/2 arc secant of the absolute value of u plus 1. I'm playing plus c. I don't know where I got the plus 1 from. So that we can call 1/2 arc secant of the absolute value of e to the 2x plus c. Now this is fine. If you want, you can kind of flaunt your understanding of absolute values and recognize that an exponential is never going to be negative, so it actually does not have to, in this case, have an absolute value. It would be completely correct to write it without the absolute value. So either of those is equally acceptable. Okay. Now, where we have to get really creative here. If we think maybe, can we say u is the inside of that radical, then the du is going to be negative 2x. Well, we have an x, but we got that extra plus 3 as well. What are we going to do with that? Well, here's the cleverness. We're going to split it apart. So we are going to write that as the integral of x over the square root of 9 minus x squared, and then a plus the integral of 3 over the square root of 9 minus x squared. Now these are going to be two very different integrals. The strategy we're going to use on the first one is what we just started. We're going to say u is the inside of that radical, 9 minus x squared. Du is a negative 2x dx, and so dx is going to be du over a negative 2x. So this integral is going to be the square root of u, and the dx will replace by our du over negative 2x. We have that x in the numerator to account for those powers of x, and so that is going to become a negative 1/2 integral, and I'm going to call that u to the negative 1/2 du. So that's just an ordinary power function. We're going to add 1 to the exponent, multiply by the reciprocal of our new exponent. That will be a negative u to the 1/2. That is, it's going to be a negative square root of 9 minus x squared. Now, back to that second integral. Now here we cannot use that same u substitution because we don't have an x there. So this is going to become an inverse trig function. Because we have a square root and it goes constant minus the power of x, this is going to become an arcsine. So we got that 3. Inside that radical, we're going to factor out the 9. That's going to leave us with a 1 minus x squared over 9 dx. So we can take that 3 outside. The square root of 9 comes outside as a 3. We'll cancel that other 3, and so we're going to get 1 over, and we've got the square root of 1 minus x squared over 9 dx. For this one, the u, So this is our 1 minus u squared. Our u is going to be x over 3. That makes du 1/3 dx and makes dx equal to 3 du. So this integral is going to become, we're going to get our 3 du to replace that dx, and it's going to be a square root of 1 minus u squared. So the 3 comes outside the integral, and we get what hopefully is becoming a little more familiar. That is going to be our arcsine of u, and so we're going to bring it down here and call it 3 arcsine of, what did we call that? X over 3, I guess, plus c. What a long, involved, complicated integral, but kind of fun. Okay, there are more complications. Now we're going to complete the square. Who could forget completing the square? So our process, our thinking process goes, well, could we let u be the entire denominator? If we did, the du would be a 2x minus 4, but we don't have an x in there, so that's not going to work. So our go-to then is to try to think of an inverse trig function. Well, that doesn't look like, it doesn't have a radical, so really the only thing where you could think to maybe work would be something that would be an arctangent. Can we make that look like a 1 plus u squared? And the answer is yes. But what we want to do first is complete the square in that denominator. So, if you remember, and you may not, we're going to go x squared minus 4x. We're going to leave a space here and push the plus 9 out because it's not that perfect square that we want. We're going to take half of the middle term. Half of negative 4 is negative 2. The sign isn't going to really matter because when we square it, it's going to be always positive. So negative 2 or positive 2. Half of 4 is 2. 2 squared is a 4. I'm going to add 4 in there. Then I'm going to turn right back around and subtract the 4 back out. Let me squeeze that over. So I'm going to add 4 and subtract 4, which is really just adding 0. But this is going to improve our situation because now this part right here is a perfect square. It's always going to be x, and then whatever that sign is, minus in this case, and the number that comes next, you can either think of as half of that or the square root of that. Those will agree with each other. That's going to be 2, and it's going to be a perfect square. And then we get the negative 4 plus 9. That's just whatever it is we get, in this case, a 5. Okay, now believe it or not, we're on our way towards a u squared plus 1. So we need to make that 5 into a 1. So we're going to factor the 5 out of the denominator and pull it all the way through out here. That's going to leave us with an x minus 2 squared over 5 plus 1. Believe it or not, that's progress. This we are looking at as our u squared plus 1. So our u is going to be the square root of that x minus 2 squared over 5. That's going to be x minus 2 over the square root of 5. Let me write that a little more clearly. Square root of 5. Now, this x minus 2 over square root of 5, you don't have to write this out, but you want to train your brain to see that as 1 over square root of 5x minus 2 over square root of 5. The key is, what is the coefficient of x? Because when we take its derivative, du, the derivative of the constant is going to be 0, but the derivative of a constant times x is going to be that constant dx. And so our dx is going to be the square root of 5 du. Okay, so here's where we are. We pulled out that 1/5. The du we're going to replace by the square root of 5 the dx rather, we're going to replace by the square root of 5 du. We now have that denominator is a u squared plus 1. That square root of x can get pulled out, so it's square root of 5 over 5 integral du over u squared plus 1. That's the integral we want because that's going to be our arctangent of u. So that's going to be a square root of 5 over 5 arctangent of our u we said was that crazy x minus 2 all over square root of 5 plus c. Wow. There's a few steps to that one. Let's try another one. Okay, so we are going to add another complication. We're going to find the area of the curve bounded by 1 over 3x minus x squared, the x-axis, x equals 3 halves, and x equals 9/4. I don't really know what that graph looks like, but the radical is positive, so it's going to be something above the x-axis, and we're going to try to find the area under the curve from 3 halves to 9/4. So that's going to be an integral. We're going to integrate this 1 over the square root of 3x minus x squared dx from 3 halves to 9/4. Oh boy. If we try to say u is the inside of that radical, then du needs to have that power of x, which it doesn't. We don't have that power of x. So that's not going to be our strategy. So now we're trying to think, is it some kind of inverse trig function perhaps? And now it's not really totally recognizable, but you can see that there's a minus x squared in there. That's going to suggest to us that it's actually going to become an arc sine. And we're going to try to make that into a 1 minus u squared. So here's how we're going to do that. So we've got this 3 halves to 9/4, 1 over. Now in that radical, I'm going to rearrange the order and call it negative x squared plus 3x. So, and I'm going to not write the limits here for a minute. So rather than equal sign, I'm going to make an arrow, which gives you a little bit more forgiveness in the AP world. So then we're going to, in that radical, factor the negative out. Now we can't bring that negative outside the radical, but I just want to be able to complete the square inside here. So I'm going to take half of the middle term, square that, and that's going to be the number that we're going to add in here, that 9/4. Now that 9/4 is getting multiplied by that negative 1, so I've really added in here a negative 9/4. So I'm going to turn right back around and add that 9/4 so that the net change is 0. Oh boy. So I'm going to now rearrange the order. So I'm going to write the positive term first in that radical. That's the 9/4 minus, and now we have a perfect square. That's the way we were doing all this. That's going to be x minus, and half of 3 is 3 halves, which is also the square root of 9/4. This is progress. Now we want to make that be a 1, so we are going to factor out that 9/4 in the radical. So we're going to take out that 9/4. That's going to make the 9/4 into a 1. To divide by 9/4 is going to leave us with a 4/9, x minus 3 halves squared, all inside that radical. Now the 9/4 can come outside, it gets square rooted, becomes 3 halves. It's in the denominator, so it'll come all the way out here as a 2/3. the reciprocal. So now we're looking at 1 over the square root of 1 minus 4/9 times x minus 3/2 squared dx. Well, this we're trying to see as our u squared. So that means our u is going to be the square root of 4/9 is 2/3, and the square root of the x minus 3/2 squared is going to be the x minus 3/2. That is going to make du, so the coefficient of x is going to be 2/3 x, so its derivative is going to be 2/3. That is going to just cancel. Actually, that'll just be a constant. So when we take the derivative, it's just going to be a 2/3 dx, and our dx will be 3/2 du. Okay, we're making progress now. So we had our 2/3 integral. The dx we're going to call 3/2 du. We have in the denominator the square root of 1 minus, and that's just going to be our u squared. So we can see that our 3/2 and 2/3 are going to cancel, and so we get an integral that we wanted, which was du over the square root of 1 minus u squared. So we know this is going to give us, I'm going to put it down here, our arc sine of u, and we're going to go back to our values of x. So our u was, where did that go? Our u was, oh, here we are. It's that 2/3. So it's the 2/3 and x minus 3/2. Remember, we had limits on this thing. So we're going from 3/2 to 9/4. 3/2 to 9/4. Okay, I'm going to slide down a little bit here. So we have arc sine of 2/3 times 9/4 minus 3/2 minus the arc sine of 2/3 times 3/2 minus 3/2. Oh boy. So arc sine of 2/3, see, 3/2, if we multiply top and bottom by 2, that's going to be 6/4. So 9/4 minus 6/4 is 3/4. So that's going to be an arc sine of, we can cancel there, it's going to be 1/2. So an arc sine of 1/2 is the angle whose sine is 1/2, and that's going to be pi over 6. Okay, we're making progress now. This is going to be the arc sine. Well, 3/2 minus 3/2 is 0. The angle whose sine is 0 is 0. And ta-da, there is our answer, pi over 6. Very good.